So, good evening. So, we'll start with complex analysis today. Right? So, this is one of the most easiest topic. The word is complex, but the topic is very simple, and the shortest syllabus among the entire mathematics optional syllabus goes for only this complex analysis. The concepts are very simple and very minimal. Right? So I just wanted to address your questions. So you tell me your questions first, then actually I'm going to address one by one. Got it? Yeah. So marks equal weightage. So each topic carries equal weightage. Right? So you need to answer 5 questions, and out of 5, so 5 into 50, total 250. Right? So for that actually the weightage that is distributed is equal to all the 8 questions. Got it? So in this actually weightage, second one is books to follow. And any other questions? Classes, it's very small. So very few number of classes, I think hardly 10. So 10 to maximum 12 classes. Any other questions? Right? So, and the focused areas. Subtopics. Right? So these are the questions actually I am going to address one by one. First of all, let me list down the entire syllabus. So the first thing is analytic function. The second one is Cauchy-Riemann equations. Cauchy's integral, sorry, Cauchy's theorem. Cauchy's integral formula. Power series representation of analytic function. Taylor series. Singularities. Laurent series. Cauchy's residue theorem, contour integration. So this is the broad syllabus. Right? So how many of you have already studied this complex analysis during your graduation? 3 years back. So can I assume everybody studied complex analysis during your graduation? Not studied, Nitya? Forgot? Okay. So this is one of the most easiest topic, and this is a must topic. Why? Because eventually we are going to start fluid dynamics, wherein the fluid dynamics is completely dependent on this complex analysis, completely. So without complex analysis, you cannot think of fluid dynamics at all. So if you understand this complex analysis pretty well here, you will be able to solve most of the questions from fluid dynamics, right? So that's why this is not only from the complex analysis point of view, you have to understand this topic even for the fluid dynamics point of view also. So that's where it is very, very important for us. So the reason why we are going to use is the analytic function, right? So this concept which we are going to use it as part of this complex analysis, that is one thing. And along with that, so the other part is the CR equations. So these are must to construct an analytic function. If you know the real part, you will be able to construct the imaginary part. Or if you know the imaginary part, you will be able to construct the real part with the help of the CR equations for an analytic function. This is the most important aspect that we are going to use as part of fluid dynamics. So that's why you have to understand these two very well as part of fluid dynamics. And then the questions that are going to be asked mostly from these parts. One is the power series representation. Power series representation of an analytic function, Taylor series and Lorentz series. So in the presence of singularities, you will be able to express the series in terms of Lorentz series. Without the presence of the singularities, you will be able to express the series in terms of Taylor series. So this is the concept mostly asked as part of the first question or the fifth question. So mostly the compulsory part. So in the compulsory part, actually, these parts are presented. And the last one, this is the place, Cauchy's residue theorem, Cauchy's integral formula, and then along with that, the contour integration is the one which is very, very stressed for the tougher questions. So this contour integration plays very critical role in the mains part. Mains part we mean that is so optional questions are there, right? There the weightage of the topic will be high, and there actually contour integration, Cauchy's residue theorem, Cauchy's integral formula. So these are the parts that are going to be asked there. Got it? So compulsory part mostly it is asked for the Taylor series or Lorentz series, and this is a basic understanding. Sometimes, so the questions that are framed even from the CR equations also, these CR equations plays critical role in constructing the analytic function. So these parts are also very, very important. Got it? So to summarize, you cannot leave any part of this syllabus at all. But quote and unquote, this topic is very, very easier topic. So that's why, so you cannot take a chance, because if you target this topic, you will be able to answer most of the questions. Clear? Got it? So do you have any questions from this analysis? Okay, right? So the book for almost every part of the syllabus is the B.S. Gravel Higher Engineering Mathematics. So I am going to follow. So this is one of the very good book to follow, but actually only thing is, I think recent editions are sufficient enough to follow the entire topic, but older editions, right? So there is a little bit of problem wherein the contour integration part is not covered elaborately. So covered elaborately we mean the models are covered, but for practice purpose he has given every problem as part of the exercise, not as the solutions. That is why you find a little bit difficulty in solving the exercise problems. So, but in the recent editions, he solved some of the example problems, which you will be able to understand very easily. Right? So I prefer to use B.S. Gravel. Got it? So do you have any voice problem? I don't think there is. Yeah. Right? So this is the syllabus. Now, so classes actually, so each class actually is one part. So that is analytic function. As part of the analytic function, limits and continuity also will be tested. So limits and continuity also I will be covering as part of analytic function, because this is the base requirement to find out an analytic function. On top of that, so if the derivative exists for a complex function, then we say the function is analytic. If the derivative doesn't exist, then we say that the function is non-analytic, right? The major difference between a normal function versus a complex function is a normal function usually in the form of y is equal to f of x. Edition of B.S. Gravel. So any recent edition you can take it up. So, but actually I studied long back around 2003. That time actually it is not covered fully. Now actually recent editions, maybe after 2010 you can find anything better. Got it? So y is equal to f of x. But coming to the complex function, so if you try to analyze this y is equal to f of x, that's what we call this as the real analysis. Now, what we are going to analyze is not so simple like this. Now, what I have done is, that is u plus iv. So, any complex number can be expressed as x plus iy format. Got it? So, x plus iy format. In this x plus iy format, this entire thing will be treated as a single variable like x. X is a single variable here. But here, two different variables together is treated as a single variable called z. This is the complexity. That's exactly the reason why we call this as complex analysis. So, two different numbers together is treated as a single number. Now, exactly in the other way, y is equal to f of x, right? So, what I have done is u plus iv. So, this is also a single function is equal to f of z. Now, this is a complex function. This is a complex function. Now, our entire topic is just based on this understanding. Got it? So, which we are going to deal each and every part, assuming this part. Here there are two different parts. This part we call as the real part, and this part we call as the imaginary part, or the complex part, or the conjugate part. Got it? So, this is what we are going to analyze. Now, the focus areas of this topic, as I said earlier, one is the Cauchy's residue theorem, Cauchy's integral formula, contour integration. These are the parts you have to concentrate more to cover very good number of marks in this particular topic. Got it? These are must. Cauchy's residue theorem, contour integration, and Cauchy's integral formula. Here, rest of the things are the just this part is for the compulsory question, Taylor's expansion and Lorentz expansion. The syllabus is very simple. That's why you will not take much of the classes for this. I don't think even 10 classes will take it for it. Let us see how many classes it will take. But quote and unquote is you need to understand this topic pretty well to understand fluid dynamics. Got it? So any questions on this analysis? Any questions? Anybody? Okay. Now let us see. First of all, today actually being the introductory class, I will be analyzing the syllabus and then I will be introducing the basic concept that you need to understand before starting our topic. So in that, first of all, I wanted you to address my query, right? What is this I means? What is this I? In a complex number or a complex function, this I comes into picture. What is this I? Square root of minus 1, imaginary number, any other answer? So, how can you justify that I is equal to square root of minus 1? Can you justify this? Somebody justify I is equal to square root of minus 1. Why I have to take square root of minus 1? Any answer? Okay. Now let me address this query. See this. So the meaning of I is multiplication with I for any number, for any real number. Will rotate the position vector of the real number in anti-clockwise direction. For 90 degrees without changing the magnitude. Of the vector. So this is the meaning of I. Got it? Right? So it's not, we don't know. So this is the definition of I. So what it means for us. Now see this. I just wanted to represent a complex number on the xy plane, or this is called xy plane, and this is also called a z plane. Both are same. Z plane we mean any random number if you put it. This is just a complex number representation. This is as if like drawing a position vector to this point, and this position vector, what we have represented here, let us say this is x comma y are the coordinates of this position vector. Then in vector format you can represent the same position vector as xi plus iy, xi plus jy. So this is the position vector of this. Now in case of complex numbers, we have only two different directions. One is the x direction and another is the y direction. But in case of vectors, we usually treat three-dimensional vectors. So that's why there are three different directions that are associated. Hence, you have to classify each direction separately with the corresponding unit vectors I, j and k. But being we are dealing with only the xy plane, which means you need to represent only two different dimensions. So you can avoid ij and you can keep only one value, because one is already known to be the real axis, which is nothing but the x-axis, and there will always be the y direction. So this is x plus iy. This is what is usually treated as a complex number z. So this is completely a 2D geometry. So no relation to 3D. So that's why we treat this number system completely differently rather than a vector. Now here, this vector, if I multiply with I, then suppose if I multiply this xi plus iy, then I will get a vector of x plus iy. Then I have multiplied with I. Then this vector, the same vector, is getting rotated in anti-clockwise direction for 90 degrees. This is R1. This is I times of x plus iy. Got it? Now actually I will justify why this I is equal to square root of minus 1. Here, this is the real axis and this is the imaginary axis or the conjugate axis. Now let us say I have calculated a value, that is I have represented on the real axis a number a. Then if I multiply with I, then this a is getting rotated in anti-clockwise direction for 90 degrees, and this number or this point I represented as AI. Now if I again multiply with I, then the same thing is getting rotated for 90 degrees in anti-clockwise direction, and this point is, that is AI into I, that is A into I square, and this is equal to minus A. This is exactly the reason why we treat I square is equal to minus 1. See this is plus A, and this is the opposite vector to it, that is minus A. So plus A and minus A, there is 180 degrees phase shift here, right? So that's exactly the reason if you multiply two times with I, that is I into I, it is rotating for 180 degrees exactly in the opposite direction. Hence this will be I square is equal to minus 1. Yeah, Ix minus Y, exactly, correct. See this. This is x plus Iy. Now I have multiplied with Ix minus Y, right? So Ix minus Y, which means minus Y plus Ix. Don't get confused with the xy letters. You always treat I as the reference. Here notice this, the magnitude in the negative direction is the real part. This part is minus Y equivalent, and the imaginary part is the vertical value. This part is x. So this is minus Y and this is x, which you have got the value by multiplying x plus Iy with I. Got it? So that's the real part is minus Y and the complex part is x. Got it? Okay. So this is x is equal to, sorry, z is equal to x plus Iy. We treat as a single number. That's the number we call as the complex number. So if it is a variable, this is complex variable. So z is a complex variable. Clear? Any questions on this? So I hope you understood this concept. If you multiply with I, it is rotated in anti-clockwise direction for 90 degrees. Again multiply with I, it is rotated again for 90 degrees. In total from the original it is 180 degrees. That's why this is A and this is minus A. So this I square multiplication is replicated with minus 1. Hence I square is equal to minus 1, or I is equal to square root of minus 1. So if you again multiply with I, then this will be minus AI. If you notice, this is plus AI, this is minus AI. And if you again multiply with I, then this is minus A into I square. Again I square is minus 1. Minus into minus will be the plus. Hence this value is plus A. Got it? So now you can justify that I square is equal to minus 1. This is where the complex number originated. And as if like it is the normal algebra, there is something called complex algebra. This complex algebra again deals with the variables, but these are complex variables. Now here, the fundamental problem with the complex number analysis, complex variable analysis is you need to represent two different planes. Why? Because if you wanted to express the plane like this, suppose I have the function y is equal to f of x. Here, one independent variable and one dependent variable. So there are two variables here. Hence, you need 2D geometry to represent a complex, to represent a y is equal to f of x function, which is a real function. But suppose if I give this function u plus iv is equal to f of x plus iy. Now this is a complex function. In this complex function, two independent variables are there and two dependent variables are there. Now to represent all the four variables together in a single graph, what is the geometry you need? What kind of geometry you need? What is the dimension of the geometry? Is it 2D or 3D? Two dependent variables, two independent variables. Anybody? Tell me what dimension you need. Is it 2D or 3D? No. So you need, this is where the limitation comes. You need four-dimensional geometry to represent a complex variable function. This is where the problem comes, right? So that's why here the whole analysis, whatever we have done in case of real analysis, is applicable for 2D. Now here, this is extended for 4D. Now, imagining a four-dimensional geometry or imagining a four-dimensional graph is very, very complex. You cannot think of or you cannot imagine it. So that's why people thought, and then finally, so they concluded that this can be divided into two different two-dimensional geometries together. So this will come automatically together. Got it? So you can note down this. I'm going to analyze this, how we are representing with the four-dimensional geometry. Great. Now see how this four-dimensional geometry impacts for us. So as we are not able to imagine a four-dimensional geometry, what we have done was, so these two together I will treat as a 2D, and then these two together will treat as again 2D. So 2D plus 2D total 4D. So that's the reason here one region we call as, this is X and this is Y, and this is what we call as Z plane. And this Z plane, each point is a complex number for us. Now each point is associated with two different variables. One is the real and another is the imaginary. Suppose this is A and this is B, then this is Z is equal to A plus IB. Now this A plus IB can be anywhere. That means if you select one more point here, it may be A1 plus IB1. So this is a different point, but two different numbers together are coming to that point. Now, in case of real function, what we have done was, this is x-axis and this is y-axis. Then y is expressed as a function of x. That means for each value of x, there will be a corresponding value of y. This is how you will be expressing. Now here, for each value of x, that's what we are stating. But here, you cannot treat as for each value of x. It is for each complex number, which essentially means that you are associating two different numbers together into a single number called z. So, hence, each point here will represent a complex number, and that's why when we deal with the complex numbers, we always tell the region. So, we always state region. This is very, very important. We don't say that the domain or range of the values. Got it? Here, domain is treated as a single value. Suppose domain for any function y is equal to f of x, you can express as domain as the R. That means it is from minus infinity to plus infinity. So there are a set of values from minus infinity to plus infinity, but which will represent only the one value, that's called x. But here, the set of values or the domain is constitutes with two different numbers for each point. So that's why we always have to treat the domain as a region rather than a single point or a single line. Got it? Now, for this set of all the values, suppose if you associate a new function called w is equal to f of z. Here, w is a function of z, but z is represented with infinite number of points. And then all the points together constitute a single region. And this region we say this is the domain of the function w is equal to f of z. Now correspondingly, for each value of z, there will be a corresponding value of w. Now, if you want to plot the value of w for each value of z, then there will be a real value and there will be an imaginary value here together. So that's why you have to construct one more two-dimensional geometry. That is, this is u and this is v, and this is what we call as w plane, or sometimes it is called as uv plane. So this is a plane again. Now for each value, there will be a calculated value somewhere here. For each value here, there will be a calculated value here. It may be a single valued function or it may be a multi-valued function also. So for each value there may be a single value here or there may be multiple values also depending upon the type of function what we have defined here. So maybe this is the region of domain. The range may be somewhere in this region. We don't know what kind of region it is. That depends on the function w. Clear? So this is how actually you represent two different two-dimensional geometry together into a single function. So that is W is equal to f of z. So it seems to be very small, but it constitutes 4-dimensional geometry. So each is a region. Got it? So the toughness comes here. Earlier, when we want to find out y is equal to f of x, then if you want to find out the limit of f of x for any value of x is tends to a, then you will be finding the left limit and you will be finding the right limit, and then you are trying to associate together, and then you can state whether the limit exists or not. But here, if you wanted to approach a complex number, that is limit z tends to a is a complex number, f of z, then here the approach is completely different. This made our complexity. So here, z actually here, what you have done, x tends to a. That means a plus and a minus. That is the left limit and right limit we have analyzed here. Here, there is nothing like that. There are infinite different directions. Suppose if you take this point as a, this can be approached from this direction, from this direction, this direction, this direction, or whatever may be the direction you can think of, you can approach that point. Got it? So now it is your responsibility to test all the infinite directions for the existence of limit. Clear? So this is where the complexity started. Now, if the limit exists and the function is continuous, continuity also you have to check exactly in the similar manner. And then if the derivative also exists, then we say that function has the analytic function. So the analytic function has multiple advantages. So, but understanding whether the function is analytic or not, this is the complexity that is involved. So whatever I have discussed in this class, these are very much needed to understand the complex analysis. Do you have any questions on this? Any questions on this? Is it clear? Yeah. So Kavya, anyway, so tomorrow actually I am going to deal with the complete topic. Today is just an introductory topic. So I have introduced the topic and the basic understanding whatever is needed to start the topic. So the conditions for analytic function, which we call as the Cauchy-Riemann equations, that completely takes one class, 1.5 hour class. I am going to take it. Yeah. Any other questions? So the order, the way we follow is, we start with the continuity and limits check. That is first. And then the conditions that are needed to verify whether the function is analytic or not. If it is an analytic function, how to find out the derivative. And then from there, we will try to understand, if you know the real part, you will be able to calculate the imaginary part. If you know the imaginary part, you will be able to calculate the real part with the help of Cauchy-Riemann equations. And this is what is exactly has almost infinite number of applications for this. And this is made the complex analysis is a must for engineering. So if you know the real part, you will be able to calculate the imaginary part. If you know the imaginary part, you will be able to calculate the real part for any analytic function. This is the condition. So you have to identify whether it is analytic or not. If it is analytic, then the Cauchy-Riemann equations are the one which will help us to find out the real part or the imaginary part, depending upon if it is one given, the other part will be known. So the applications being, one is here in case of fluid dynamics, right? If you notice, that is the potential lines and the streamlines will always be exactly perpendicular to each other. So these are the potential lines. And these are the streamlines. So these are always perpendicular to each other. As I told you earlier, the real part and imaginary part are always separated in an anti-clockwise direction for 90 degrees. So that's exactly the condition. So if this is u and this v will be exactly 90 degrees from u. So if this represents u, then this will automatically represent v. So our applications are mostly targeted. If you know the potential line, you will be able to calculate the streamlines. These streamlines are the ones which will show the direction of the fluid flow. Got it? So most of the times actually these are the questions that are going to be asked. This is one application in fluid dynamics. If you take electrical engineering, right? So the equipotential lines and the electric field lines will always be perpendicular to each other. So that's why if you know the equipotential lines, you will be able to calculate the electric field lines. If you know the electric field lines, you will be able to calculate the equipotential lines. Again, it is the same application, exactly follows the same principle. This is another application. And if you take the heat flow again, the heat flow lines and the heat potential lines will be exactly perpendicular to each other. This is exactly the reason most of the engineering applications are just dependent on this complex analysis. So, but to summarize, the entire thing is just understood. If you know the real part, you will be able to calculate the imaginary part for any analytic function with the help of CR equation. That's what is the target. But it has got infinite number of applications. The same concept got infinite number of applications. This is one major applications in engineering. And another part is the contour integration. So the contour integration is the one which solved most of the engineering problems. For example, if you take control systems, in control systems, identifying whether the system is stable or not, right? That is very, very crucial. If the system is stable, then actually you will be trying to analyzing the stability. So you will be trying to analyze the performance of the system. But if the system is unstable, there is no point in analyzing the performance because the system itself is unstable. Now identifying whether the system is stable or not for complex systems, it's very, very tough. But with the help of this contour integration, there is something called a technique called Nyquist criterion, which solved most of the control system problems with the help of the same concept called the contour integration. This is one major application. Got it? And the same contour integration, some of the engineering integrals, which we will not be able to solve it, those integrals we will be able to solve with the help of contour integration. That is one major advantage. Got it? Clear? So as we are dealing with the calculus of this complex numbers or the complex variables calculus we are dealing, we are always needs to find out the derivative and the integrals. Now these derivatives and integrals for finding it out, right? So first of all you have to verify whether it is analytic or not. If it is analytic, the derivative exists. Automatically if there is a derivative, as we are dealing with the calculus, the counter application which we call as the integral values, you will have to find out. Now it's not simple like the real integral value to find out, but the complex integrals are a little bit tougher to find out. So that's why to solve certain pattern of integrals, there were certain theorems that brought into picture. Those theorems, especially the major and the fundamental of all the theorems of integrals, is the Cauchy's theorem. So the Cauchy's theorem will give the base principle. Suppose for any analytic function, if there are no singularities, then f of z into dx will become 0 if there are no singulars in the region of integration. Here, notice that I am stating as the region of integration, not the range of integration. That is very must to understand. So that is the fundamental. The extension of the Cauchy's theorem is if there are any singular points, that is where there is a possibility of becoming denominator 0, then there are singularities that exist. So these singularities will cause the Cauchy's theorem to fail. So the extension of that is Cauchy's integral formula came into picture. So that is again targeted in understanding the integral of the complex function. These integrals, why do we need? We just need for the purpose of solving unknown integrals in the real analysis and solving some of the engineering problems like Nyquist criterion and all, right? So that's why these derivatives, integrals, series expansion, contour integration are must, or analytic function, CR equations. These are all very much needed for engineering analysis at the same time for our purpose. As fluid dynamics is one topic for our syllabus, so that will be most of the problems will be solved with the help of this analytic function, which I am going to deal in upcoming classes. Clear? Any questions on this? Any questions? Any other questions? So I think so with this I would like to conclude today's class. Tomorrow I will start the actual topic. with the limits and continuity of any complex function. So, but for that you need to understand these basic concepts already. So that's all for today. Yeah, thank you.